Hello, everyone. My name is John Toman. I am the chief scientist at Certora. We are a company that focuses on providing security solutions in the Web3 space. This includes audit and also formal verification using the Certora Prover, which we're actually open sourcing rather soon. And probably by the time you're seeing this, it's already been open sourced. What I'm going to be talking to you about today is something that is in some ways complementary to the auditing and the formal verification I've described just now, and involves monitoring protocols once they're deployed on chain. And particularly, we're going to talk about how we can do this using another open source framework that we just released called Safeguard. So when I'm talking about monitoring invariants, I think it's important to start by discussing what invariants are and why they matter. Once we've sort of set that groundwork, we're going to then move on to exactly what this looks like with Safeguard, and then very quickly finish up with a comparison to other tools. Because at the end of the day, Safeguard is about monitoring. So, of course, it fits into the broader ecosystem of things like Forta, Hexagate, and so on. So what are invariants and why do they matter? Why do we want to monitor them? Well, if you've ever discussed formal verification or security audits, or even probably developed a non-trivial Web3 smart contract, you may have heard the term invariant to describe some property of the system. For example, the invariant of the lending protocol means that it's always solvent, or something like that. More generally, an invariant is just any property that must hold at a point of quiescence. And I'll go on and describe quiescence in a little bit. And the property here is just a formal logical predicate over a system state. Now, this is a more, formal definition. But of course, an invariant doesn't have to be, strictly a logical predicate. It could be in plain English, and you often find these sorts of things scattered about in documentation comments. They are a description of a system's health. They are a way to describe all of the possible states of the system that are considered good. And if a state falls outside of an invariant, if the invariant doesn't hold, that is, then that means something has gone very wrong. So before we dive into exactly what these invariants are, I think it's important to say why an invariant is only supposed to hold at points of quiescence. And why shouldn't an invariant always hold? As I just said, an invariant describes the good states of a system. Shouldn't we always want the system to be in a good state? Well, let's look at the very simple invariant, right? We have some very simple token here. And an invariant here says that the sum of all user balances should equal to the result of the total supply function. And again, here we've stated our invariant as natural English, but we could also write it using fancy math notation if we wanted to, but the meaning is ultimately the same. Now, this invariant says that no user has managed to gain access or gain control of more tokens than they should have, and also it means that no one has somehow lost tokens, that all of the tokens essentially are accounted for, that the contract knows about. Now, again, I think it's perhaps self-evident why this is a good property to have hold. But why don't we want it to hold always? Well, let's take a look at this transfer function. And we can see at this point, the invariant is actually violated, right? At this point, the balance of the sender has been decreased by the amount that's being transferred, but the balance of the recipient of the transfer has not yet been credited that amount. So at this exact moment in time, the invariant is violated, but that's okay, because the next line, this line that adds the amount to balances to the recipient, restores the invariant. So this is why we don't want to insist that the invariant holds at every single possible point in time. It's okay for us to break the invariant temporarily, provided that once we reach these points of quiescence, it is restored. So what is quiescence? It's a very fancy way of saying the system is at rest. And another way of saying when the system may be interacted with, or, for example, there's nothing in flight happening, right? Any current outstanding external call into the contract has finished, and it's now ready to receive new input from external actors. So this would be at the end of a transaction. For example, at the end of a transaction, the message that was received from some external user has been fully processed, and as a result returned, and any changes to the current state applied. And so while the system is actively servicing a request, as we just saw, the invariance may be temporarily broken. But it should be the case that once the transaction is finished and once your external call has finished executing, the invariant should still hold. Now, there might, of course, be exceptions to this. It's possible that You have some special configuration where you allow the invariant to be broken during some administrative actions or governance proposals, but this is a good rule of thumb. Now, what quiescence is specifically depends on the protocol system. Now, I said as a good rule of thumb, it should hold up the transaction at the end of every single transaction, but you might need actually more points of quiescence than this. A great example for this is if you have reentrant functions. If your protocol has reentrancy, then you should make sure that the invariant holds when you make an external call out to some other contract, because that other contract could call back into you. And you don't want to enter your protocol or your contract in a broken invariant state. Now, again, you might actually be able to do this. This might actually be okay. But it is going to be protocol dependent and logic dependent on whether or not you do have reentrancy. Maybe you always have reentrant lock, so it's fine, and so on. But it is, I think, fair to say that for the majority of cases, after every single transaction, that should be a point of quiescence, because there's no outstanding request, there's no ongoing data processing. Any state changes that are done in your system is, again, at rest. And so that is a point where you expect your invariants to hold. So now we spent a lot of time talking about the when of invariants. When do we expect these invariants to hold? So let's return to the question of what invariants should hold. And that there is not actually really a good universal rule of thumb. It will necessarily depend on your protocol or your system. Again, the invariants for a lending protocol will look very different from an AMM, for example. But a good invariant is always one that provides a precise description of system health. And this goes back to the example we saw with the token, which is to say that the sum of all user balances should equal the sum of the total supply value. Now, this is not sufficient. This invariant by itself does not suggest that if this invariant holds, the protocol is in a good state. There might be other ways that the protocol could go bad. But it should be the case that a broken invariant almost always means something has gone wrong. And so that's why invariants are so useful when reasoning about and thinking about system health, because they concisely describe and precisely describe what you expect the system state to be, again, at a point of quiescence. So again, we talked about what it means if that token invariant doesn't hold. Again, the user has lost tokens, or they've managed to mint more tokens or names than they should have. These are all bad for them. And there can be other types of invariants for more complicated protocols. And we're actually going to see some examples of those coming up in a little bit. But for example, a lending protocol might have a solvency invariant, which says that the amount of collateral posted should be greater than or equal to the total amount of outstanding debt. Again, if this invariant is violated, the protocol is now underwater. There are more outstanding debts than there are collateral to cover it. Or, for example, you could imagine if you have a marketplace, an important invariant might be independence of accounts. That is, any withdrawal or deposit for one user should never be able to affect the account of another user on the same exchange. And again, if this invariant is broken, that means that users are able to now affect each other's funds when they really shouldn't be. So all of this is a sort of to simplify all of this. It is to say that broken invariants are bad. A broken invariant strongly suggests that the protocol is broken in some way. Now, there is actually another possibility here, which is that the invariant's wrong, that you failed to account for some, edge case, or you did not account for some other possibility. Now, we're going to assume for the time being and for the rest of this talk that our invariants are correct, but the ways to sort of iterate on and find correctness for invariants is itself almost a meta process. The correctness of your correctness invariants is sort of a famously hard thing to formalize. But there are ways that you can sort of test this and iterate to those, and we're not going to talk about them in this talk. But assuming that your invariants are correct, a broken invariant suggests that, again, either you're being hacked or you have a bug in your code, that you expected this invariant to always hold, and now it doesn't. So that's bad. So when we say we want to monitor invariants, we want to literally check and have invariants that are stated for a protocol or a system, and then always check to see whether or not that invariant holds or not. And if it ever doesn't hold, that suggests that a live protocol or system has somehow reached a bad state, that something bad has happened. So I'm going to go on a quick digression here to discuss actually a real-life invariant. And this is going to be for the Aave protocol. Now, I'm going to skim over a lot of details here. And I'm the sake of that, I'm going to skip some important details. But high level, this is roughly what an invariant for the Aave protocol looks like. So the Aave lending protocol has a list of reserve, and each reserve, which corresponds to some on-chain asset like USDC, Tether, etc., has an associated A token and an associated variable debt token. An A token is a receipt for suppliers to the protocol, people who supply liquidity to be borrowed, effectively get an A token as a receipt for their deposit. And then the variable debt token is issued to when people borrow from the protocol as sort of a representation of their borrow obligation. So the invariant here, again stated in English, is that there should be enough assets to cover the suppliers. So breaking that down a little bit, what we want to say is that for any reserve, the current liquidity, that is the amount that has been deposited by suppliers but not borrowed against, plus the variable debt token total supply, must be at least as large as the A token total supply. Now, what does that actually mean? A good way of restating that is to sort of say, if every single debt was magically just immediately repaid, if we somehow forced every outstanding borrower to repay their loans, that plus the remaining liquidity would be enough for every single A token holder to cash in their A tokens and get the underlying asset back. Now, again, there's perhaps a mathematical way to represent this, and there's actually also a way to represent this in code, as we'll see in a little bit. But this is I think, a nice example of a real-world invariant that is intuitively makes a lot of sense, right? You never want to be able to have a bank run. That means that people can't withdraw their amounts. This is very good invariant for a protocol to have. So let's actually dive into the details a little bit of the Aave protocol. Again, I'm not going to go into a lot of detail here, but enough to sort of make the rest of this talk, to give context to the rest of this talk. So the main entry point for interacting with the Aave protocol is a pool, which has three fields: a reserve count, a reserve list, and the reserves. Now, the reserves list is actually just a mapping, which maps a reserve index to the address, and that address is mapped by reserves to reserve data. Now, the actual reserve indices are the values between 0 and reserve count exclusive. So if reserve count is, I think it's around 30 something now, then reserves list will have a mapping for that integer to a specific address, and that address the reserve struct. So the reserve data struct then has the A token address, the variable debt token address, and the virtual underlying balance, and a bunch of other fields that, again, are not relevant for what we're discussing now. The A token address is the associated A token. The variable debt token address is the address of the variable debt token for the underlying reserve. And then the virtual underlying balance is the field that records the liquidity in the pool. That is the amount of asset that has been deposited but not yet borrowed against. And so with this information, we can actually write code to check the sort of natural language description of the invariant we saw previously. It's quite simple. Now, there's actually a lot of details here that I'm leaving out. There are other parts of this computation that need to be taken into consideration that I'm omitting here for space on the slide. But we can see that the core of the invariant here can be expressed in a couple of lines of code. We can iterate from the reserve indexes from 0 to reserve count, get the address of that reserve, get the reserve data associated with that reserve, and then execute this assertion. And if this assertion ever fails, that means we have a violated invariant, and that is bad. Now, why am I going into such deep detail about this Aave invariant? The point here is to really drive home that invariants are we started out saying that invariants were this logical predicate over system states, and I'm actually trying to show that invariants can be concretized and realized as actual something you could write code to check on some real world state for a real world protocol. So I hope I've convinced you now at least that invariants are important. So how do we monitor these invariants? Well, there are two key ingredients here. One is an executable invariant check, like the snippet of pseudocode we just saw. It takes the current state of the protocol or system and then indicates whether or not the invariant is violated or holds. So in our previous example, we had an assert statement. So if we finish that code without ever having an assertion violation, that means the invariant holds. But we also need an infrastructure for invoking this invariant check and providing the current state, the sort of the driver, if you will, for the actual invariant check itself. Now, as I spent some time discussing previously, the executable invariant check is necessarily bespoke. There's not going to be some reusable invariant because even as we saw with the Aave example just now, the actual layout of data in storage itself can be different between different protocols, even if they're actually implementing the exact same logic. But what about an infrastructure for doing this invariant check and being this driver that I described about? Well, there are many, many possibilities for monitoring out there that do this exact role. They take some transaction data or other relevant event information and invoke some code that perform some sort of check. Forda in particular has these agents or bots that try to scan live transaction or block information to determine whether or not something fishy is happening. And you can definitely do invariant monitoring in these ecosystems, at least in Forda. And we have actually done that as a form of comparison. And we'll discuss that a little bit more later. But what if we wanted to monitor as close to the EVM as possible? So when I say close to the EVM, like what do I mean and why would we want this? Well, by integrating tightly with the EVM, we can see transactions as soon as they are broadcast on the consensus protocol. There's no delay that you might have with other monitoring where you first have to ingest something into a side network like the Forda network and then do that. It happens as soon as the block is broadcast, you basically run the invariant checks. You can also access and mutate internal EVM state during the checks. And this is actually pretty important, as is getting a consistent view of state during the execution check. If you are executing quite close to or tightly integrated with the EVM, then you can be guaranteed that, unlike in other cases, if you're relying on an RPC provider, in that case, you could be in the middle of a check, be making queries to an RPC provider, asking for the current balances of some contract or getting the current storage field. And meanwhile, that RPC provider has now actually seen yet another block. And now suddenly it's giving you different answers. So that consistency of always knowing you're getting the same view of state during the invariant check is quite important. And we're going to return to this point in a little bit. And finally, speed is quite important as well. So with all of these reasons for wanting to be tightly integrated to the EVM, the answer is pretty obvious, which is to implement and execute the invariant checks within the EVM itself. Now, at first blush, this sounds crazy, but it's so crazy it actually works. It is surprisingly easy to do. I will actually show you the entire implementation required to do this in a couple of slides. And spoiler, it fits on one slide. So it's actually not that hard to do in terms of the tooling. And after the initial learning curve of learning the APIs and how to interact with the low-level infrastructure of the EVM, it's an incredibly powerful tool for monitoring. And we'll discuss that in a little bit as well. And so that is exactly what Safeguard is. And that's how we're going to discuss doing invariant checking with Safeguard. It's an open source framework. The GitHub link is here on today, the day that we're recording this, we made it open source. It provides the glue between the invariant checking code that checks the invariant, that's the executable part of the invariant checker, and the EVM, and the transaction information, block information, and so on. And there are some very light abstractions to help out too. That is an area that we are actively developing right now. Stay tuned for both later in this talk when I discuss what that is and future pull requests on the Safeguard repo. Now, one thing that I think is really important to mention is that there is no one single EVM. The execution layer of the Ethereum ecosystem is defined by the yellow paper. And anything that faithfully implements the yellow paper is an EVM. Safeguard, though, in particular, modifies the Go Ethereum implementation, which I'm going to be calling Geth, which is what it's commonly referred to. So we did not build our own EVM for this, but rather we're using, I think the most widely used Ethereum implementation out there. So that means that at the very least, you can be sure that we haven't introduced or have not faithfully implemented the EVM semantics. We're simply reusing the semantics, the execution semantics rather, of all of the most widely used Ethereum client. Now, there's one final thing that I hope should be obvious, but it bears repeating here. which is that we are talking about running a modified version of Geth. The changes that are done as part of Safeguard should be completely transparent to the execution/consensus layer. But even so, never use this to stake or be a validator in the network. The Go Ethereum implementation has safeguards to detect if you diverge from the head state, and it basically hard crashes, which is a perfectly sensible thing to do. So there is even some safeguards built into Geth against this, but better safe than sorry. Don't risk your ETH trying to stake doing this. It's very possible to run a Geth node without staking anything and simply to follow the network and run a node that just downloads the data but doesn't participate in the consensus mechanism. So before we talk more about what implementing a detector looks like in Go, we need to discuss a little bit the nitty-gritty of how blocks are broadcast and the EVM processes that block information. So after the upgrade to proof of stake, what's called the consensus client is now a separate executable from the EVM. And this is the program responsible for communicating with the other nodes in the network and determining what the head of the blockchain should be, participating in committees and quorums and all of that. It does this completely outside. It runs at a completely separate address space. It downloads block information from the gossip network. It takes a proposed block. It then makes an RPC call to the execution client, in this case, Go Ethereum, locally. So this is a local RPC call. The execution client, again, in our case, Geth, executes the transaction data from the new block that was being considered by the consensus client, checks to see that the resulting state root hash matches what is held in the block header. And if it does, it reports this back to the consensus client. It basically checks the work of the block being broadcast. And is at this third step that we come in and we sort of hook into the Go Ethereum implementation. We have added a small bit of code to the part of the Go Ethereum client, which actually executes on each of these state transitions to actually do the invariant checks. And as promised, here is the entirety of the implementation to call an invariant checker. Now, I'm playing a little bit of sleight of hand here in that there is a lot of other admin code aside from this that implements a lot of APIs and provides some glue code, but this is the actual core of the safeguard logic. This comes basically right after the loop that executes all of the transactions in the block passed by the consensus client. And once that loop is finished, the blockchain, the local version of state, is in a state that reflects the most recent series of transactions. And we take that and we pass it out to what we call the safeguard impl queue. This invariant checks call, which I've pointed to here, is the call out to the invariant detector code. And here you can see that we're passing in both the state database, which is the low-level object in Go Ethereum, which provides access to account storage, contract code, balances, what have you, along with the log information and some other information as well. So the actual implementation of the detector logic isn't here. It's inside of this invariant check. So when I say that it's only 22 lines to do the checking logic, I mean it's 22 lines to actually insert the logic into the call to that logic into the EVM itself. The actual logic of the invariants can be arbitrarily complicated, as we'll see in a little bit. So where do these invariants come from? Where do these detector implementations come from? Well, they are currently dynamically loaded from a shared object file. So sorry, Windows users. They implement a simple interface. The entirety of the interface is shown here. This actually has no simplification. This is the entirety of the implementation. And there is a little bit of admin functionality that is also built in. That's some of the stuff I said that was there, but not actually included in that 22 lines of code. And that includes things like dynamic reloading. You can send a privileged message to the Go Ethereum client to ask it to reload your invariant check logic from another shared object file. This is really crucial for debugging. Otherwise, if you had to restart Go Ethereum every single time you wanted to change your invariant checking logic, the warm-up time is non-trivial. You can also temporarily pause logic or restart it, and you can also set log levels dynamically as well. But just those pieces and these invariant checks call, and that is all you need to implement a detector. You need to export it with a special name from your dynamic object file, the documentation of which is all in the GitHub repo, so I'm not going to go into it here. But suffice to say, if you provide an object that implements this interface, then you have provided exactly what is needed to be integrated into that we saw earlier on the previous slide. So I'm going to very quickly return to the Aave invariant that we saw previously. This is the one we saw where we had this executable way of checking the invariant that all the A tokens were possibly could be honored by the lending protocol. And it turns out we can actually almost completely transliterate this into some Go implementation. So this is actually taken from the Aave lending protocol detector. This is available inside of the open source repo. So here I am leaving out a lot of code, but you can actually see the basically the skeleton of what we saw with the pseudocode. We first read the reserve count, we get the native int, then we iterate from 0 to the reserve count, eventually read the reserve data, and so on and so forth. Again, because we're having to do this all low level, it ends up being quite more verbose than the simple lines of pseudocode we needed. Because again, you have to deal with things like packing of storage fields and serializing and deserializing call data information and so on. Currently, all of that low-level interaction has to be done manually, but there is work coming soonish that should actually auto-generate wrappers for you to make this much, much easier and less error-prone as well. So this is the body of one of those invariant checks function. And what can you do inside of one of these invariant checks? And the answer is almost anything. This is the beauty of running inside of the EVM. You can access arbitrary contract storage. You can look at historical log data. You can call view functions. You can also, if you're very careful, crank contract bytecode. Now, this is actually a very cool feature. You can, because you have access to the state database, you have read access to that as well, which means you can overwrite a specific contract's addresses bytecode with whatever you want, and then call another function. And as far as the execution of that other function is concerned, that is the ground truth. You can effectively play God. You can also execute and simulate arbitrary transactions and pretend to be anyone, any possible address. You can fake any address or any call from any sender. This is, again, very similar to something you can do in something like Foundry, where you have the pranking, but you're doing this inside the EVM itself. Now, again, this has to be done with care because you are working with a live copy of the Ethereum state database. Luckily, the Ethereum state database has very good rollback functionality. Every mutation you make pushes something onto a journal, so it's very easy to roll back snapshots. It's quite cheap to do that as well. And it's important to mention that all of these are done with the overhead of a Go function call. And that the reasons for that are going to come up in a little bit, but if you were trying to make several accesses to storage, asking to call a view function, you're doing this with RPC calls to some other remote RPC provider. Every single read of storage, every single execution of a view function has the overhead of transiting the network, serializing and deserializing the JSON parameters and so on. Whereas in Safeguarded, by integrating tightly within the EVM, all you have to do is just call the Go function. It just happens right there, all in the same address space. So let's actually go on a little bit more why this matters. And we're going to talk about another example invariant, this time for a protocol called Uniswap. Now, I suspect almost everyone viewing this talk has heard of Uniswap, but just in case you haven't, this is a DEX deployed on both Ethereum and many other chains, and it allows trading between two assets in a pool. Liquidity providers can create positions by adding liquidity to a specific pool and depositing tokens with the pool in doing so. And so every position corresponds to amount of the underlying assets. And if you go into the Uniswap interface, you'll be told sort of, here's how much your position is worth in terms of the two underlying assets of a specific pool. Now, this can change as the price of the pool changes and the tick changes and a lot of other complicated Uniswap math that is really quite complicated and out of scope for this talk. But the invariant, again, is sort of intuitively makes good sense. When you create a position, you are depositing tokens with the pool, and you are having some virtual representation of that value that you've deposited. And so the protocol must therefore hold sufficient tokens to cover every position. Every person who deposited their tokens with the pool and received back the liquidity in return, if they all decided at the same time, hey, I decided I want to trade my liquidity back in for the 2 underlying assets that I gave you originally, the protocol has to be able to serve every single one of those requests. Again, a bank run shouldn't cause people to lose out their money. So again, another way to say this is that if every liquidity provider cashes out their liquidity, then the protocol must have enough tokens to do this cashing out. Everyone should be able to get their tokens back. Now, the data layout for Uniswap, again, I'm leaving out a lot of details here. The key point here, though, is that the pool manager, which is the main entry point for creating these positions, has a field called pools, which is a mapping from pool ID to pool state. Pool state itself is a struct that has a field which maps every position key to a position. The pool ID, by the way, is a hash of the underlying token addresses with other information. That information is stored nowhere else. It's actually only in the pool ID, it's hash. And position is itself a struct that has information from which you can compute the amount of tokens owed. Again, the actual details of that computation are not relevant to this, and so I'm not going to belabor it much further here. But the pseudocode for this invariant check looks something like this. We start with some required balances for all the possible tokens. We iterate through all of the pools in the pools field. We iterate through all of those pools positions. We reverse the hash of the pool ID to get the underlying token, and then also compute the price, or rather compute the amount of tokens owed to that position in terms of token 0, and then compute the amount of tokens required for the other asset in the pool. And then you would go through the required balance map and assert that the total holdings of the pool is greater than or equal to the required balance. Now, 2 things should stick out at you in this. One is this. You obviously can't actually reverse a hash. If we could do that, we would be out breaking every cryptographic protocol in the world. So, here the pseudocode is doing quite a bit of hand waving to hide what's actually going on here. But there's actually a way to get around this. The other is actually here. Well, in the pseudocode, we're iterating through 2 mappings. But for those of you who know Solidity, there's no built-in way to iterate through all of the key value pairs in a mapping. Unlike in a language like TypeScript or Java, where you can iterate through a map, mappings, just from the way that they're represented in Solidity, provide no built-in way for you to track all of the keys, unless there's some side structure that you might find. There's a data structure called the enumerable map, which also stores the keys, but that's something you have to opt into, and Uniswap has not opted to do that. So how do we actually manage to implement this? And here actually logs come to the rescue. Here, logs actually come to the rescue. The Uniswap protocol helpfully emits a log whenever a position or a pool is created. These logs include important information. For example, it'll include both the pool ID saying, hey, we just created this pool, but it'll also include with it the addresses of the underlying tokens that are being swapped inside that pool. That's the only time this information is available. And likewise, we can look for all of the events that are emitted that say, hey, a position was just created, or this position changed their liquidity, or they did a swap, whatever. Cache that in memory, and then when we need to iterate over the pools, we just iterate over all of that. And again, this is the power of the safeguard approach. By both running as a dynamically loaded object, it has its own sort of piece of memory where it can cache the state. And we can also interrogate the native log data. So for each of those blocks, you saw that we passed in the log information. And this means that the detector can keep a running total, or rather a running collection of all of the positions and all of the pools to make that for loop we saw previously possible. Now, I should also mention that this doesn't, the statefulness of this make it hard, raise some availability concerns. What happens if the node has to go down or restart? Well, in that case, again, because we're running inside the EVM, we could in principle just scan the log history again. Although actually in our implementation, we query Etherscan because they have indexes that make that much faster than trying to do it natively. But in principle, you could still do all of this inside of the EVM itself. This is actually also why I have been really making a point to drive home about speed here. because some of these pools have thousands of positions, and there are many pools as well. And so if we were implementing this detector outside of the EVM, and we needed to query the state of the pool and the position and all of that using RPC calls, we would have to make thousands of RPC calls. Now this has two problems. One, if we had to do this with JSON API, you very quickly hit your API usage limits, most likely. And we'd also fail to finish these computations within the block time. And again, this matters because this comes back to the consistency question. While we're doing this computation, if we are taking longer than the block time, the RPC provider might now see a new state and start giving answers about different answers about what the state of the protocol is. And so again, this is why speed is so important, both because it makes these sorts of very computationally and IO intensive, if you will, operations feasible, but also means that we can run them in sub-block times, which is 12 seconds. And so this, I think, actually is a good point to make a comparison with other tools. And another way to frame this is saying, couldn't we do all this in Forta? Well, the pranking we would probably have a harder time to do. But something like the Aave checker, you absolutely can. You can set it up to query an RPC provider to answer questions about the current reserves. They'll get all that information, again, using RPC call. But the trade-offs there are, well, again, mostly speed related. Because our version has no RPC calls, we actually execute that Aave check about 150 times faster over Forta. Now, again, the implementation we have is not hyper optimized, so it could go faster, but it's still orders of magnitude. A lot of that comes from the network overhead of having to make these external calls. And this is not any sort of indictment of the Forta implementation or anything like that. It's just the inherent overhead of having to make RPC calls to some client and just having to go over the network. That's just always going to add non-trivial overhead. One other thing that is not so obvious is that by executing within the EVM, we have access to EVM primitives sort of built in. So UINT 256 math is very, very easy to do in a way that mimics the EVM semantics, because the UINT 256 library used by the detector is exactly the same UINT 256 library that was used by the Go Ethereum. And it's also very easy to mutate and simulate transactions and mutate state. And as I think I mentioned, there's no inconsistencies you have to deal with an RPC provider. We talked a lot about what happens if the RPC provider gets ahead of you, but there's also the problem that the RPC provider might not actually have seen the block that you're talking about right now. So you might be asking it questions, and it's sort of behind you in terms of all that. Now, the cons of running Safeguard are, again, the great power comes great responsibility. It becomes very possible to completely trash your Ethereum state. Again, the Go Ethereum design is done in such a way that this is quite recoverable from, but it's still something you don't want to have to deal with. It's dealing with crashing Go Ethereum because you accidentally mutated the state. But a more sort of logistical issue is that currently running Safeguard requires you to run a Go Ethereum node. Now, that is, spinning up a beacon chain. There's plenty of guides on doing that, but you need non-trivial hardware. You need, I think the current recommendation is at least a 2 terabyte SSD and have pretty significant amounts of RAM. So this isn't something that you could probably be really running on a laptop. Also, currently, the last couple of points are kind of related in that the interface exposed by the invariant checking right now is quite bare bones. So you're currently responsible for making all of those storage accesses yourself. I think I mentioned that we are currently working on writing code that will, writing a tool that will auto-generate that storage interaction code for you. But as of right now, as we're recording this talk, it's still quite a bare bones interface, which makes it a little harder to deal with. But as I've hinted about a couple of times, there are a lot of future directions that we're considering to include with Safeguard. One is adding support for hosted languages. So, for example, you can embed a JavaScript runtime into Go. In fact, the Go Ethereum executable already includes a JavaScript runtime. So that means you could actually write the detector code in JavaScript, provided you are given a sort of a host API for querying into the Ethereum state. You could similarly do something with WASM, and that opens up the possibility of writing your invariant checks in Rust, for example, or any language that compiles down to WASM. More robust APIs I've mentioned a couple of times, especially with the auto generation of some of the wrapper code. And I think we're also interested in exposing Safeguard outside of the loop that executes transactions when they're received from the consensus client. So some sort of simulation, which is pretend that you were to execute this transaction. If you do that, doesn't violate this invariant. Or you could sort of scan the history of a protocol and say, was this invariant ever violated? This would be a great way to test your invariants. If you have an invariant and it's violated at some point in your past, well then either you had an invariant violation and dodged a bullet, or perhaps you're invariant. So that is the future of Safeguard and a quick whirlwind. A lot of the code snippets I've shown here were pulled directly from the implementations of the Uniswap and Aave detectors. You can find those in our GitHub repository. And with that, I need to thank everyone else in Certora who's helped out on this. I'm the one giving the talk, but this was very much a team effort, especially in clarifying the details of how some of these protocols worked and really spinning up the infrastructure for making this happen. So thank you all very much. Thank you for watching. I appreciate this, and you want emails there, feel free to reach out via email or ask a question in the comments, or reach out on X if you want to learn more about this. Thank you all very much.